तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in the previous lectures we worked out a few examples. So, with those examples it must be very clear what exactly a processor is doing. Okay. Now, let us just quickly review and then move on to the next part of the series, that is about the memory. Fine. What did we start with? We started with saying that by and large we have what is known as von Neumann's model, that is von Neumann's specifically called stored program digital computer. Okay. The architecture of this is what is there in most of the computers, even in present day. So, the architecture about this. The specific thing in the stored program digital computer is essentially it is the program and the data, both of it are stored in the memory. Okay. So, the computer takes the program, executes the program instruction by instruction, okay, instruction after instruction, it takes it and then executes that, and then it moves on to the next instruction. That is what has been going on specifically. Okay. Now, for executing one instruction, right, the computer will be invoking what are called a series of micro instructions. If okay, a series of steps in one specific implementation, you may call them as micro instructions. Okay. You may also do without micro instruction, it is a different thing altogether. Okay. Then these micro instructions, what do they specify? Essentially this thing gives a small step in the execution of an instruction. So, just as program is executed instruction by instruction, an instruction gets executed step by step, okay, step by step, and this small step essentially corresponds to, in one implementation, a micro instruction. Okay. So, it is a small step. Good. Now, the controller will be issuing the necessary control signals, so that for the execution of the instruction a path may be set up. Now, that path depends on what exactly the instruction says. Suppose you have an arithmetic instruction, then the path will be such as to carry out that arithmetic part, okay, meaning to execute that arithmetic instruction. So, the architecture essentially consists of setting up a data path for executing an instruction. Okay. Now, it is only path over which the data flows, and then for setting up this data path the appropriate control signals. So, that is generally called data path control signals. Okay. Now, there are two parts of the processor. that is 1, which is essentially concerned with the data path, will include the necessary arithmetic and possibly logic circuits, and specifically one component will be called an arithmetic logic unit. Okay. Then the other, this is one part of the processor. The other part of the processor which is concerned with issuing the necessary control signals. So, that is the controller or just the control unit. Okay. So, together this ALU and controller, this forms the processor or what we may call as a central processing unit. This is what we had seen. If this controller were implemented using micro instructions, then we call it as micro programmed controller. There are other ways of implementing this also. Good. Normally in a course on computer organization, lot more may be said about this arithmetic processing also. I personally feel it is not necessary. I will just explain the basic behind this and then leave the rest to your working out. Okay. For instance, recall what whatever we were talking about the ALU. We said an ALU, just we took as an example, which can execute a few, I think I said something like 16 arithmetic instructions, okay, 16 arithmetic, that is an ALU is capable of carrying out some 16 arithmetic operations and let us say I said 16 logic operations. Okay. These are the operations, and the way you arrange these operations would depend on precisely what exactly the instruction that is to be executed. Okay. Now, instead of this 16 arithmetic instruction, you may include for instance the basic things add and subtract, okay, add and subtract. So, these are two basic arithmetic instructions. Now, there can be some more complex arithmetic also. The next step in even in arithmetic would be for instance having a multiply instruction or having a divide instruction. Suppose we want to add this multiply instruction and divide instruction also, then you need the necessary unit for this. For instance, we may say add multiplier unit and add a dividing unit. Okay. You might say that, but then is it always necessary? No, mainly because for instance multiply can always be carried out with some series of additions, is it not? Which means multiply can be carried out with repeated additions. Okay. Now, this is one what we call as an algorithm. Now, instead of repeated addition, for instance the usual paper and pencil method with which you are familiar, what is that? That is shift and add, okay, shift and add algorithm or method. Now, in the repeated addition, let us see what is it, which is straightforward. A multiply will be having a multiplier, okay, and a multiplicand. So, multiplicand and multiplier. Now, these are the two data. Okay. Now, let us call multiplicand as A and multiplier as say B. Then the repeated addition would mean add A B times. That is, for instance, if you have something like 5 into 4, to get this particular result multiply, that is the product. Okay. It's the shift and that is a repeated addition would basically say add 5 4 times. Okay. This particular thing can also be got like this, is it not? So, add 5 4 times. So, that is what we mean by saying repeated addition. Good. Instead of that, you can also carry out, now this holds good for any data, right. So, let us say if you have a data like say 120 and then multiply it by, let us say 12. Okay. The same thing holds good, 120 must be added 12 times. Now, let us see the next algorithm, which says shift and add. We are quite familiar with this, there is no problem about that, right. What is that? Generally what we do is, we now this is the multiplicand and this is the multiplier. So, the algorithm would be, look at the multiplier, see, I mean take only one of the n digit of the multiplier. So, we take this least significant digit, then multiply that with multiplicand. So, in this case we will be getting 240 and then with this digit is over. So, move on to the next digit and then multiply that. In that case you have to shift the multiplicand, because 1 into 120 whatever you have, you actually shift and put it, is it not? You shift that, you do not put it right below, but you shift it, then you add, right. So, we will be getting 1440, right. So, now this multiplication algorithm can be based on the repeated addition method or based on shift and add. So, the software related to this, because what is an algorithm? Algorithm essentially tells the step by step how a particular operation must be carried out. Okay. Now, when you say it is repeated addition, then it is enough if we have an adder. Now, when you go for shift and add, we need an adder and then we need the appropriate shifter also, right. Good. And then how exactly we carry out 2 times 120, which again is multiplication, again it is a repeated addition, right. Now, of course, this problem will not be there if you are doing with binary number, because the binary number is going to be 1 or 0. Now, let us just see what we mean by that. Supposing we have a multiplicand 1101 and then a multiplier 10, that is binary, then let us just do as per the shift and add. Then it says the multiplier consists of 2 bits, take the least significant bit. Now, actually I am speaking out the algorithm, take the least significant bit. If it is 0, then if you multiply that with the multiplicand, which will result just in zeros. So, we can say if the multiplier bit is 0, then the temporary product or intermediate product is 0, then move on to the next significant bit. If it is 0, then repeat it, because it will again be 0. If it is 1, just write the multiplicand, okay, but shift it appropriately as I have done here, then you add these. Okay. Now, there you have the binary product. Now, compared with this non-binary multiplication, it is easier. Why? It says if the multiplier bit is 0, just the intermediate product is 0. If the multiplier bit is 1, take the multiplicand, but then depending on the position of the multiplier bit, you shift as many. Now, with this particular one you just have to shift by 1 bit and then you add. Now, this you can work it out for other numbers, fine. Once you have this algorithm, then there is no problem, agreed. So, we need not really add the necessary arithmetic circuits or units, right, because just like multiplier is repeated addition, division can also be looked at as repeated subtraction, can be carried out. But then there is an advantage if you have a special hardware circuit, let us say for a multiplier or for divider, because this way the implementation will be faster, because anything done through software means step by step, and step by step would mean more time, right. Whereas, here you can see that it will be done very faster. Okay. For instance, even between these two, repeated addition and shift and add, repeated addition will take more time, whereas shift and add will take relatively less time. So, actually it is the speed of implementation, okay, which would determine whether you should have a special unit. Now, what we are talking about is, let us say, a multiplier. Okay. Once you know what the algorithm is, then it can be implemented, and then implementation of that particular thing is essentially a matter of deciding on a few things like the register size. Then as the algorithm says, whatever you have to do, those things will have to be done appropriately and generate the necessary control signals. So, essentially it means for any arithmetic processing, first the algorithm must be decided, and then after you have chosen the algorithm, then it must be implemented. Okay. Implementation of that. Now, implementation of that, once you know what the algorithm is, then it is just based on the logic design principles with which I am pretty sure you are all quite familiar. Okay. Basic, it will boil down to a simple logic design work. Nevertheless, a few more points deserve to be noted here. What is that? Suppose we have an 8-bit CPU. Okay. Suppose we have an 8-bit CPU, then it means the internal registers of the processor CPU will be 8-bit, the ALU will be 8-bit, and so on so forth. And even this particular example what we have taken, the multiplicand is a 4-bit number and the multiplier is a 2-bit number. Now, it is all right for us, we are quite familiar with this, but then when it comes to hardware implementation, okay, where exactly which of the 4 bits in the 8-bit it will have to be fit in, and which 2 bits of this 8-bit will have to be fit in. For instance, if you talk about a multiplicand say register, it will be 8 bits. Okay. Now, actually in the least significant of this, say 1 1 0 1, this will have to be entered, right. Now, that is for the multiplicand. Similarly, for the multiplier, this will have to be entered not anywhere, but then in the last. Okay. And then after looking at it, we may keep shifting here. For instance, multiplicand can be an 8-bit number, multiplier can be another 8-bit number. Now, when you multiply, you will be getting what? As much as a 16-bit result is a possibility. We really do not have 16-bit registers anywhere. So, these are certain things which will have to be taken into account in the design. Okay. So, in other words, we may say in the design actually the size of registers, okay, the size of registers that you have, because we may not really know what is the size of the multiplicand and the multiplier, it will depend on the problem, but we have to necessarily handle only an 8-bit number, means maximum 8-bit multiplicand will be there, 8-bit multiplier will be there, but the result will be 16-bit, which will have to be accommodated in 2 registers, and the data path control signal must generate so that 8-bit part of the 16-bit result, one part, least significant part will be one register, the other one must be in the other register. So, the control signals must be generated, right, from that point of view. And another thing, yes, as I said, in the case of 16-bit result, now it will go out of this particular register. So, we are moving it. So, that is called an overflow condition, right. So, conditions such as that, okay, for instance an overflow condition, it is a possibility. Okay. So, how exactly we are going to handle this overflow situation? And then the other point is, so far we have not taken the sign of the data, did we anywhere? No. So, but then we know that numbers, sign numbers will also have to be represented. So, we have to take into account the sign of that, and so the what is called as the signed arithmetic is also something which we have to actually bother about, correct, signed arithmetic. So, so far we are not bothered about the signed part, right. Now, the simple thing, let us say now if you add say 2 numbers, something like let us say plus 9 and minus 5, it really amounts to a subtract operation, is it not, right. Plus 9 and minus 5 you are adding, it actually amounts to subtraction. And now, in the case of multiplication, suppose you multiply say minus 9 and minus 5. So, the result will be actually positive, the product will be a positive number, which means the algorithm that goes for the magnitude part of the number is different from the algorithm that is needed for the sign part, because any number will consist of the sign and then the magnitude, is it not, magnitude. So, there are 2 parts. So, the algorithm for the magnitude is just what we had really considered in all these things. We are not taken into account the sign, agreed. So, the algorithm for the sign also must be taken into account. So, one is the size of the result and the registers, because physically these registers are present, right. We have to bother about the size, so that we will not lose any part of the result. Okay, overflow is one such situation. Another thing is the algorithm related to the sign. So, these are certain things which will have to be taken into account. And another important thing is how exactly a number is represented, right. If you take the sign also into account, then as shown here you can always do it like plus 9 and minus 5, that is sign part and then magnitude part, as I was telling. And then you also have other forms of representation, that is known as complement representation. I am pretty sure all of you know about that. So, there is another form, that is a complement representation, and we all know that there are at least 2 things, that is called 1's complement and 2's complement, okay, representation, 1's complement and 2's complement representation in binary, okay. That also is there. Then in case the number is represented say in 2's complement, then the algorithm will change. That is, we have a different algorithm for 2's complement representation, another algorithm for 1's complement, another algorithm for sign magnitude, and so on. So, these are the things which must be considered, and once you have considered all these, then it just boils down to a simple logic design problem. Okay, it is nothing much to do with how exactly the CPU deals with it. Okay. If the special multiplier circuit is there, then the multiply command will activate the multiplier circuit, right, and inside the multiplier circuit the necessary control signals will be such that the data path within the multiplier will be set up for the resultant product. If multiplier is not there, then it will make use of the general ALU chip, and then through repeated addition or some such thing it will be carrying it on. So, that means the moment you have an algorithm, it just tells you the software part, and there may or may not be a direct hardware implementation of the algorithm. Okay, good. So, that is the particular thing which we have to take that into account. Okay. In other words, the data path design can be enhanced by considering all these additional units, that is what we mean. Okay. That is, the data path, whatever you have considered earlier is the main thing, and the data path design can be enhanced by having these extra hardware units. So, essentially it is a question of enhancement, and as I said, with special purpose hardware. In other words, hardware implementation of software. Now, why do we do all this? As I already mentioned, it is essentially to see that the speed with which we want the arithmetic, okay, or any other operation can be carried out with the respective unit. Good. To round up our discussion on the processor, what did we see? We said essentially talking about the stored program computer. So, you have the memory. Okay. Now, let us just represent the memory as the block. Now, the memory contains both instructions and data, and then we said that the processor takes instruction from the memory, because the memory includes the program. The program consists of series of instructions. The processor takes, okay, the instruction from the memory. We said that it does by addressing, that it sends a code, essentially that is the address of the instruction, and the instruction it gets from the memory, and later on after it gets that particular instruction code, it decodes that, and internally it generates certain codes, okay, and which may result possibly in fetching some data. So, the processor in that case will have to again do a similar thing, that is, the instruction it takes and it generates a set of codes. For instance, these codes can be anything, even the micro instruction for instance. Okay. Let us not bother what it is, and assuming the processor continues to access the memory, this time for getting the operand or the data from the memory, because that also is available in the memory, right, because essentially that is what we said, stored program concept. Okay. Now, the processor is accessing the memory, gets the instruction, that is what is our basic cycle. We said earlier, the instruction cycle consists essentially of fetching the instruction, that is the first phase, and then interpreting or decoding that particular instruction, and in that process only it will internally generate the necessary codes, and then it goes into the execution phase or the execute phase, and if necessary after it interprets the instruction, it may fetch the data also, that is the operand fetch, and that is what we are seeing here. Okay. So, good. And then, so it fetches an instruction, internally it would tell what else it wants, they say let us fetching the data and so on. After the processor has everything, from the instruction it knows what is the operation to be done. and it has the necessary data, then it executes the instruction. At the end of that instruction cycle, that is after it executes, this will be generating certain information. Generally it is called the state of the processor. Okay. This do not confuse this with the state of the state machine. Okay. Again it is some codes which indicates the state of the processor. Let us say the instruction is an add instruction, and after it had got the two data A and B, the addition may result, let us say, in a carry or an overflow or something. So, that state it has got to register, right, because based on that the next instruction will have to be fetched and so on. So, that is the state we are talking about here. Now, this part of the processor may be appropriately called an instruction processor, okay, an instruction processor, and this part we may call appropriately as the data processor. So, IP or the instruction processor does something and the DP or the data processor does something. Now, it is possible that one part of the CPU is concerned essentially with fetching and decoding instruction, and another part of the CPU essentially concerning itself with the data part, okay, and the execution of it. Now, this particular architecture is what we have seen as von Neumann architecture. Okay. The von Neumann, as we said a little earlier, is a stored program digital computer architecture. That is what it is. And even to this day, as I said, 85, 91, 90, 90 plus % of all the computers, they still follow this architecture. Good. The first major change in this can be, of course, you can start from anywhere. Let us say you split this memory into two, this particular memory, suppose I split into two, and I keep the instruction part, okay, the instruction here and the data here. This is also memory. Now, you can see that the two parts of the processor can carry on some activities independently. Why? Because if it were a single monolithic block, then when the instruction processor accesses the memory, the data processor cannot. But now, if I keep them as two separate units, then when the instruction processor is fetching the instruction, the data processor can also fetch the data. That parallel thing is possible. Okay. This first step, that is having two different means of accessing the respective part of the program, that is instruction and data, which really gives rise to, say, a data bus separately and an instruction bus separately, not having a single common bus, had in fact given rise to what is known as the Harvard architecture, okay, in which you have these two buses separately. You have them separate so that you can carry on both these simultaneously. So, this improves the say the speed, let us say, of execution. In fact, Harvard architecture is essentially followed in DSPs, that is digital signal processing chips, because there is huge amount of computation to be carried out, okay, in the case of digital signal processing. Sometimes the data may be less, but the amount of processing is enormous. So, in those situations, it may be better to improve by bringing in, as I said, some kind of parallelism. So, that is what has been achieved here, right, by splitting and having two separate buses, an instruction bus and the data bus separately. Good. Now, this is one aspect of it. The other aspect, even without mentioning, we had already seen the circuitry which deals with the instruction and the circuitry which deals with the data within the CPU have already been segregated here. This is also some kind of parallelism, is it not? Okay. Now, this is one thing. The second thing which it automatically leads, now look at it, look at this diagram, that itself must suggest to you what else can be done. The first question is, you have one IP. Now, why have only one IP? Why not more? Okay. We have only one IP. You can have more IPs, in which case we can simultaneously fetch lot of instructions and carrying them out. Now, the same question, why have only one DP? Okay, we will ask that later. Now, if it is possible to fetch more than one instruction and carry out, then we talk about a system, okay, in which we have what is known as instruction parallelism. Okay. That is, we started with one instruction and one data, right. This thing is generally called a single instruction and single data, single instruction and single data. Now, we are talking about multiple instruction and we continue with single data. Then we talk, when we say that the system is carrying out some instruction parallelism. It may not always be meaningful, it may be meaningful to carry out parallelly more than one instruction, but it may not always be, that we will not bother about now. Now, the same thing, that is have more than one IP. Then when you have more than one IP, can you still continue with one memory block? Maybe here also we will have to have more than one memory block. Okay? We will not bother about that yet. Now, the same thing asking about this DP or the data processor. Why have only one DP? Why not more DPs? Sure. Then in which case obviously we would be talking about data parallelism. Okay. Then we will be having, say, possible single no, it may not be very meaningful, we will continue with the same thing, multiple instruction, that is we are continuing with more than one IP, and now data also multiple data, multiple instruction and multiple data. So, we can have more than one DP. Then correspondingly we can have more than one data memory. Okay. There are other issues related to it, but just look at it. The reason why I am giving this particular figure is you can logically proceed and then go on adding more and more and then try to understand what other issues this particular thing brings in, that is the main thing here. So, instruction parallelism and data parallelism, they all come from this simple thing, right. Now, all these things are made possible because of the technology. The processors have become cheaper. So, what was not possible earlier, such as having say 100 processors or so, now it is possible, okay, it has become cost effective, and so these things are also coming. But the application must support this is important, because you may not be able to carry on multiple instruction, you may not be able to carry on with multiple data processing all the time, it depends. Okay. Now, let us work out the other combinations possible here. That is, we have the instruction stream and data stream, and what has been, and then single and multiple. So, now what is left with is you have single instruction and multiple data. Okay, that is the only thing. Before we discuss these multiple things, okay, this is single instruction, single data is quite conventional. Now, just take a look at this multiple instruction, multiple data. Okay, that is fine, because you can have more than one instruction and more than one data, and then single instruction and multiple data. Anytime multiple data can be processed with one instruction and another instruction and so on and so forth. But take a look at this multiple instruction and single data. What is this particular thing? This is how we started with, but nevertheless we will take a look at it. You have only one data and then you have multiple instruction. Now, what happens at the end of this multiple instruction? Execution of one set of multiple instruction on single data will obviously lead to multiple data. So, we will come back to this. So, really speaking, this is not a practical, this will not lead to a practical system. Okay. So, generally when we talk about parallel architectures, we talk about these multiple instruction, multiple data or MIMD, single instruction, multiple data or SIMD. So, generally we talk about MIMD or SIMD architecture, SIMD or MIMD architecture as far as parallelism is concerned. Okay. Then the other one is a straightforward single thing. Good. Now, more about this we would take a look at later on. Okay. Now, this is just to give you some glimpse of parallelism that is possible, which naturally comes from this simple and you may say as a primitive block diagram, right. And then there are other issues, because when you have multiple data and even if it is single or multiple instruction does not matter, then there will be lot more than one result that will be available here. How exactly these things can be communicated to the other data processors among those n processes. Now, these are all issues. So, apart from this computation, then another issue of communication among those processors also come in. Okay. Now, all this we will possibly take a relook at towards the end of this series of lectures. Okay. Now, as a next thing, we will concentrate on how exactly the CPU in general deals with the memory, that is the CPU memory interaction. Now, before that we have already seen, rather in fact we know that CPU addresses the memory and then memory response and so on and so forth. We will take a look at the memory in detail and then the different memory hierarchies. Okay, we had talked about it maybe towards the beginning of this series. Okay, we will take a look at them and then work out the details, and then also take a look at the interaction between CPU and memory. And what about I/O? That is the third one that is left. We already said I/O is an extended memory, is it not? We have talked about it, but nevertheless we will also discuss I/O later on. So, in our next part of this series of lectures, we will take a look at the memory. Okay. So much we about CPU or the processor that we have seen, and essentially this is all that you need to remember about the processor for just getting an idea about what goes on further between CPU and memory or CPU and I/O, or even expanding it further to include all the latest things such as parallel architectures and so on.